Right, I think everyone here is back from this side is back from the break. I hope it's the same in Harvard. I cannot see the audience there, so I'll just assume everybody is back. Good, so welcome back everyone to the second part of this lecture series. So hopefully today I'll try to explain to you what a superselection sector is actually. And we go look a little bit more of the structure on these sectors that we defined yesterday. So very helpfully, Bruno explained the GNS representation that we already used yesterday. I just used that it exists. Hopefully now you know a bit more about this. Maybe one thing I want to mention. So the slides to yesterday's lecture, they have been uploaded to the website. The Harvard website at least. So you can download them there if you want to look at them again. And I will make sure that today's lecture slides will also be uploaded there. Good. Yeah, so maybe one more thing to say now. So at the end of Bruno's talk, there was some discussion about ground state of the toric code and things like this. So I hope to come back to this question, at least a related question later. So hopefully I don't forget. Right. So let's just briefly recall what we've been doing yesterday. So we considered the toric codes on the plane, on the Z2 lattice, and we constructed the ground state and automorphisms describing single anyons. So we had these path operators going to infinity. And we defined automorphisms in terms of them. And these, as I was explaining, should be the anyons. And these give four equivalence classes of irreducible representations. Right, so that's basically what I did yesterday. So these are irreducible and they're all inequivalent. So there's no unitary intertwining them. So yeah, so as Bruno already mentioned this lecture today, so that's really one of the key differences between if you look at the finite system and an infinite system. So in finite system, always these representations are always equivalent, at least the irreducible ones. But here, that's very much not the case. That's what makes it so interesting. Good. So one of the questions yesterday, so one of Anton's questions essentially boiled down to this. So how do we know that we choose these representations? Why are these the right ones? Right, so I defined this automorphisms basically because I know what it should be in the toric code, but if I wouldn't know that, well, you know, what should I do? And the second question is, does this set of representations have more structure? In particular, as was already alluded to in one of the questions in Bruno's talk, for the toric code, we have fusion of anyons. So we want to have this kind of structure here as well. Right. So that's kind of what I will talk about today. So I don't think I'll get the fusion today, but I will get it tomorrow, hopefully. But this is move this. Good. Right. So I first want to explain to you what a superselection sector is, and this hopefully also answers the question, you know, which representations should we study, which one are the interesting ones. So let me go a little bit back in time. So this goes back to already early 50s. Namely, what's the superselection rule? So consider a representation of a C-star algebra on some Hilbert space, so just any representation, and you take two unit vectors in this Hilbert space. Right, then we can define a new unit vector by just you know, taking the sum of there, but I put this face in there.
Can I show you something that's puzzling my computer?
Is there a question? Oh, is somebody?
You have to fix somebody's computer.
I have to fix. Okay, I assume there's no questions here. Right. So we can define this vector, and then, as we've seen before, we can define a state on our C-star algebra in this way. So we just take the expectation value with respect to this
acting up a bit.
I think
I sent an email yesterday. This guy Elliot Glazer, and I expected him to respond kind of promptly.
I'm not sure if I can.
I'm worried he didn't get the email. I sent it like yesterday morning.
So you can
Because
somebody
when I
maybe
pulled up the email
use.
from sent items, it's weird. I've never seen
I
this
don't
kind
think
of
I can
format. It
do it.
doesn't show
Yes.
his email address or anything like that.
Let me see.
So I think this is what you sent to him, and did he send back?
No,
Talk, question mark?
no,
Is it this one? Please, yeah.
Can you just turn the speaker off for a minute? Just.
Okay. I think yes. Okay. Thanks. Right. No, they don't have to be orthogonal. I'm not assuming that now. I just assume two different factors. For this to be interesting, you want them to be orthogonal, but yeah. Right. So you can define this state, and I say that these vectors, they satisfy a superselection rule if the state actually does not depend on the space here. So actually, I think this implies there must be an orthogonal for that to be the case. And this can only happen if the representation pi is not irreducible, otherwise it's wrong. Right. So originally, I think the example that Rick Whiteman and Wigner gave is one of is a state where one of the states describes a boson, one of the states describes a fermion, and then if you take a superposition of these two, there's like a relative phase that you cannot distinguish. So that's I do that. Right. So a slightly different formulation of this kind of the same idea. You can look at two states, omega 1 and omega 2, and we say they are not superposable if in any representation pi that contains these vectors implementing the states. So this representation containing these vectors implementing the states just means that in the Hilbert space in which this representation is defined, I have these vectors psi1 and psi2 such that omega 1 is given by the inner product of with psi1 like this, and the same for psi2. Right, so there are vectors in these states that implement these vector states, just like we saw in the GNS representation. Right. So if we, so what we can do, we can look at this linear combination of these states. So of course, I want this still to be a unit vector. So I have these conditions on these complex coefficients there. So I can define the state, and if this decomposes as a sum of two different states, or well, like this, for all these coefficients, then we say that the states are not superposed. So it's again, it's really the same idea that these you cannot observe this relative phase. Good. Right. So that's the definition. There's a nice theorem. So if you have pure states, two pure states, then they are not superposable if and only if the GNS representations are unitary. Then they are superposable if and only if the GNS representations are unitary equivalent. So that's a very nice criterion, as you can see. So essentially, well, the way you can think of this is that if we have two unitary equivalent inequivalent states, there's no maps intertwining these two things. So we cannot go from one representation to the other. Right. So maybe some comments on equivalent representation. So they have the same normal states. So if you don't know what normal means, it's not too important. So there's sort of natural topologies from von Neumann algebras. This is one of them. But yeah, so you have you can define the same states of them. And we can think of these different equivalence classes as describing different charges. So this idea that if they're not unitary equivalent, this really means if I have a vector in one state, I have a vector state in one representation, then by acting with this representation, so I act with my local observables on this vector, I will never be able to obtain a vector in the inequivalent representation. So physically what this means, if you think, for example, as this, we had this different states yesterday that are shown in equivalent. So let's take the ground state of the Toric code. That's one representation. And I take another representation that has this single anion. And this single anion representation, if I act with local operators on the GNS state there, or any vector state, I can never get back to the ground state. And I think that's intuitively that's maybe clear why that's the case, because with the local operations, you can only, well, we have this excitation there. With local operations, we can maybe move it around to a different place, but we cannot completely get rid of it. So the only way to get rid of it is if you go all the way to infinity, but that's not a local operation. So that's I think the nice physical interpretation here. And maybe this also explains why these electric and these magnetic states that we defined, why they are actually ground states, right? So with ground states, you have the lowest energy. Intuitively, well, first you might think, okay, there's this excitation sitting there that should have some energy, right? But the point is that with these local operations, we can move the excitation around, but we cannot get rid of it. So we can make the energy a little bit lower in the place where the excitation was, just by moving it away, but then my excitation will be somewhere else. So the total energy of the system will not be lower. So that's why this is a ground state. Right, so that's hopefully maybe clarify some of the discussion that we had earlier. Of course, there are many other states in this representation that we can have. So we can create other excitations in this the same state, but as we already seen before, they always come in pairs. So the total charge does not change. So this will become clear when we talk about fusion. Yeah, so these pair of excitations fuse to the vacuum, but there's one excitation that we cannot get rid of. Right. So really, we can think of these vectors in these representations as they can describe many different excitations, but the total charge of that will be the same for all the vectors. Good. So hopefully this gives me this is some sufficient motivation to so why it would be useful to look at irreducible representations of the model. But there's one problem. So there are many unphysical irreducible representations. So a general C-star algebra has very many different inequivalent irreducible representations, but most of them, they will not be interesting for us from a physical point of view. They might have infinite energy or unbounded energy from below. All these kind of things can go wrong. So we want to find sort of a criterion that tells us, okay, these are the interesting representations. And that is basically also the answer to Ante's question yesterday, which representations should we take? Right, so before I will tell you which one to take, I want to get back to my states that I defined yesterday. And we just want to see some of the properties that they have and see, is this maybe something that we can generalize? Good, so we have this notation for the GNS construction. And again, I use the opposite convention to Bruno, because Bruno first wrote the Hilbert space and then the vector and then representation. I do it exactly the other way around. But good, hopefully that's not too confusing. Right, so we have this, sorry, this should be representation-free ground state. But yeah, so that's the notation that we use. And then we define these maps, these automorphisms that introduce these factors. Right, so I realized my notation yesterday was maybe not too clear. So always this upper index indicates what the type of the representation was. So one was defined in terms of Pauli X matrices, one was defined in Pauli Z matrices, and then there was one that was the combination of the two. And this subscript here, this is just the location of the side where the end of the string is. So that's the subscript. So it's not the X of the Pauli matrix. Good. Yeah, so we don't really need this location, but it's there now. Right. So what do we have? Well, we have this GNS construction, and very similar to Bruno's example when he looked at this invariant states, we can define another. So we can define a GNS representation by taking phi 0, compose it with my automorphism, and this will be a GNS representation for the states that I defined yesterday with the single annual states. Good. So if you now take two of these infinite ribbons, I start at the same point, but they might go in different directions. So what I showed you yesterday is that using these either the star operators or the bracket operators, I can move this ribbon around from one to the other. Right. So I can always, it's always enough to do this for a finite part. But what you can see from that is that, well, actually these two states, they are the same. So by the uniqueness of the GNS representation that Bruno mentioned, there is some unitary that intertwines these two representations. And these unitaries we call charge transporters. So the idea is this row X is localized in this, say, in this direction. So this row X only acts non-trivially outside of this one on this one string, and then we have the other string. So what this V does is basically it moves this thing from one to the other side. So these are called, as I said, charge transporters. Good. So now I can state my superselection criterion. So as I said, there are many representations that are not interesting for us. So we only want to look at the representation that satisfies this criterion, which I will explain now. So first we need to choose a reference representation. And of course, for us, that's going to be the one that we get from the precision-free ground state. So that's kind of what you will see as you vacuum if you want, or if you empty space. Then I look at another representation pi. I say it satisfies the superselection criterion if for any cone lambda that I defined here, this representation pi is unitary equivalent to the ground state representation when restricted to observables outside of the cone. So this little c up there, this always means the complement of the set. So this is just everything that's localized outside of the cone. Right. So so in our example, we've seen that these representations that constructed, they obviously satisfy this, at least if we fix a single cone that contains the string to infinity, because outside of that cone, it just acts like the identity. And as I see here, so this was a composition, so I just get by 0. But we want this not only to hold for the single cone, I want this to hold for all different cones. So if I choose a cone in a different direction, I still want it to hold. And really what this is saying is that I can move my cone where it's localized. I can find something that's unitary equivalent that's localized in a different cone. That was a question.
Yeah, we say all calls with a fixed origin, or
I don't need to fix origin. No. You can do that if you want, but it's not really necessary.
I think the calls usually call with the fx any point.
Yeah. Right, so this model satisfies translation invariance. So basically, you can always move things around. So you would expect to be able to move things around. I don't assume it. So yeah, but yeah. So I don't assume translation invariance, but for this to be an interesting theory, you would expect that you would need at least some translation covariance, something like this, maybe not invariance, but yeah. Right. So maybe I should say this at this point. So I mean cone by general. So it can also have like a big opening angle, like bigger than pi, for example. I just don't want it to be the whole space. So I want it to be, there's some things to be cut out, basically. Right. So what's the interpretation? As I said, this is basically this thing captures two different things. The first one is this kind of idea of localizability. So outside of any given cone, this looks like the reference representation. Again, up to unitary equivalence, and I can move around because it holds for all cone. I can move around this region. But that's the idea. So maybe I should point that out. So as we've seen before, but it's maybe good to mention it explicitly. Our anion representations, they satisfy this, but it's no longer true if we remove this restriction to outside of the cone. That's what we've seen before. These are inequivalent representations. So if you don't restrict to observables outside of the cone, but you just look at them as the whole algebra, then they're not unitary equivalent. Right. So yeah, that's the definition. So a superselection sector is called, well, so this is a unitary regression class of such representations. And so now this should solve our problem that in general there are many inequivalent representations, but in general there are not many that satisfy this criteria. And in fact, as you shall see over today and maybe tomorrow, for the toric code, there's only 4 irreducible representations up to equivalence that satisfy it. So we've gone from infinitely many representations to 4. So that's, I think, a pretty good reduction. Right. So maybe a final comment. So this notion of a cone is not too important. You want to have some nice geometrical properties. But yeah, it really depends on what kind of excitation you want to capture. What's sort of the right selection criteria. Right. So if you would do, for example, conformal field theory on the circle, you can set up a kind of a similar theory, and then instead of cones, you would use intervals on the circle, for example. Right. Good. So now we know which representations to look at, and this is basically just a restatement of what we've done yesterday, namely there are at least 4 irreducible sectors for the toric code. So irreducible sector just means that the representatives are irreducible representations. And well, we know how to construct them. We just use these infinite paths, either on the lattice or on the dual lattice. We can define this automorphism. And by what I just told you earlier, these representations, they satisfy this selection criterion. Right, so I'm cheating a little bit here because I assumed that my paths, in my argument, I assumed that my paths started at the same point. That's not really a restriction because you can easily find a unitary, namely the path operates itself, that will move a single point to another single point. That's just a unitary in your algebra, so that doesn't change the selection criterion. Right, and the inequivalence I've indicated yesterday as well. So these 4 different sectors that we have, including the vacuum, we can all distinguish them by some circle at infinity, by a big loop. We can distinguish them. Right, and as I just mentioned before, it actually turns out that these are all of them. That's quite non-trivial, but I will say a little bit more about this later this week. Good. Right, let me get a drink. So what do we want to do next, right? So we've got these automorphisms, satisfy this criterion, and these are the anyons, but we want to define extra structure, right? These anyons should be described by a moderate tensor category. So in particular, we want to define a fusion operation, and we want to define a braided of these things. So that's going to be our next goal. So let me first define what a monoidal category is, or a tensor category. So I will use these 2 notions more or less interchangeably. Some authors make a difference between tensor categories and monoidal categories. So tensor categories would have more structure than a linear structure and things like this. So the categories that we will be looking at, they will be both monoidal and tensor in both of these things. So there should be no, whatever definition you prefer, there should be no confusion here. Right, but yeah, just let me briefly introduce the definition. So what we want to do is we want to define a kind of a tensor product on a category, and this should be the fusion operation in physics terms. Good, so what's the definition? Well, we need a bifunctor from our category together with a distinguished object, the unit, and a family of isomorphisms. So it's kind of a natural thing to do. So of course, if you can take the tensor product, you can first take the tensor product of 2 objects and then do it with the other one, or you can do it in the other way around. And of course, you want these things to be maybe not equal, but at least isomorphic. And the same for the tensor unit. So tensoring with the unit should be the trivial operation of isomorphism. Good. So these things must satisfy some axioms. For this to be well defined, usually called the pentagon and triangle axioms. I will show them in a diagram on the next slide. But first, things will be a little bit easier because there's a special case, namely if these are all happen to be the identity morphisms, then we say it's called a strict monoidal category. And our categories will turn out to be strict, most of them at least. Good, so that's the pentagon axiom. It basically tells us, if you have 4 objects, there's all these different ways that you can put the brackets. And no matter how you go from one to the other, you should always get the same thing up to isomorphism, and that's basically this diagram. The same for the unit, so you can put them in different ways. Right, so this is only for the no, just for both. Yes. Right, so then there's the famous coherence theorem by McNeil that basically tells us if these conditions hold, then the same will be true for n tensor product of n things. So if you're a tensor product of n things, you can put the brackets in any way you want. Good. As I said, we don't have to worry too much about the axioms because in our case, all the tensor categories will be strict. And before I will define it for our superselection sectors, I want to give sort of another example of a strict monoidal tensor category that's going to be quite related to the ones that we will see. Right, so here's the example. So we start with the unital C-star algebra. So the C-star is not really important here. So you can just think of star algebra. We can define the category of endomorphisms of this. So the objects of the category are the unital star endomorphisms of our algebra, and then the morphisms between them. So it's, if you see this for the first time, it's a little bit confusing because too many things are, because the morphisms are the objects and then the morphisms are intertwiners. But that's the way it is. Of course, this is very similar. Maybe it's a more familiar example. If you take a category, you can look at the functors from the category to itself. This forms a monoidal category. It's very similar to this. Right. But yeah, this is the definition. So the morphisms from rho to sigma, we usually call them intertwiners because of this. So these are just the elements in our algebra that intertwine the action of these two morphisms for all A. Right. So this is obviously a category. You can check the axioms. But first, the interesting thing is that this has a monoidal product, and it's defined on objects as just composition of the two endomorphisms. Right. So the endomorphisms, so we can compose them. I get a new endomorphism, and so that's what it does on objects. So now we need to say what this tensor product is on morphisms, so on our intertwiners, because this is supposed to be a bifunctor. So we should say what it does on these things. So if I have an S in intertwined from rho 1 to rho 2, T intertwined from sigma 1 to sigma 2, I can define the monoidal product in the following way. S times rho 1 of T, and it's a short calculation to check that this is in there. Right, so you can use this, do this calculation by using that that rho 1 is an endomorphism. So if you write it out, you will get at some point rho 1 T times rho 1 of S sigma 1 of A, and then you can use that this is an endomorphism. So it's a short calculation. It's a nice exercise to do. Right, so this makes this into a strict monoidal category. Right, there's no associators here. This is everything's true.
Compositional morphism, just multiplication.
Sorry, what was it?
The compositional morphism, just multiplication.
Yes. Sorry, that should be yes. Thank you. This is just multiplication in the algebra. That's right. Yeah.
Thanks.
Yeah. Sorry, that's a typo. Good. So that's the example that I want to keep you in mind. You to keep in mind. Yes, I think I have this on my next slide. Right. So motivated by this example and by what we know about the toric code, so we constructed automorphisms. So particularly they will be in this category end of A that I just defined. But as before I said, well, we don't want everything. So my first definition, well, my first attempt at the definition, say, is it's going to be this one. Right. So given a representation pi 0, we can define a category delta DHR, which has objects endomorphisms rho of A. So I don't need to be automorphisms, that is happy to be automorphism in my case, but that's not important. But I want them to have them similar properties as we've seen before. Namely, I want them to be localized in some cone, meaning that they act as the identity outside, well, on all observables outside of this cone. That's the first condition. And the other condition that we had is we wanted to be able to move this region around. So how can we state that here? Well, if we choose a different cone, I can find an endomorphism localized in this other cone that is related to the first one with some unitary in our representation space, BFH. So it should satisfy by this one. So this is almost the same as we had before in our example, except now we have this pi 0 here. Right, and the morphisms they are the same, but now they intertwine these things with the morphisms. We can easily see some examples of these intertwiners. So I talked about these charge transporters that move this cone around, and it's easy to check that we have this condition there. See, I've already written that down before. Good. So that's sort of the idea. So we want to define the monoidal product on this.
Can I ask a question about this?
Yes.
So when you say localized, I would have imagined to not talk about cones, but have a finite subsets. And then also like regarding the transportability, I'm worried about like what if the other cone is like really small or something, so like this one doesn't fit in or something.
So that's these are good questions. So the first question, localized. Yes, it's a good point. So local can mean sort of different things, but here I'm really thinking about the localization of the excitations. And because I have sort of this string attached to infinity, I need to have this kind of infinite region to localize thing. So because there's always this string otherwise, and that you can always detect it by crossing the string essentially, if you go like all the way around. So I need to cut out the direction in which the string can go to infinity. So that's why I need this kind of cone kind of thing. For the second part, so we don't. So the question is, maybe this cone needs to be big enough or something like this. So in our case, that's not really a problem because this, we just have this single path to infinity. So the cone doesn't have to be very wide. So we can always, either move it further in the cone or something if we need more space, but that's not going to be an issue. So if it become wider, we can basically always move it in there.
So you design for those particular isomorphisms that we talked about.
Yeah, so I can imagine that there might be some models where you would maybe need to impose sort of a minimum size of the cone or a minimum opening angle or something like this. For us, that will not be a problem. Later in this week on Thursday, I will also give sort of a variant here where the localization is not strict, but you can have some kind of decay outside there. That's a different related question.
Yeah. Just to comment on this question. So is that correct? I mean, okay, in your example, the strings were like essentially very thin, like if they have any finite size, well, it doesn't matter how thin what the size is, because first of all, whatever happens, if you go far enough along the cone, they're going to fit into that cone.
Exactly. Yeah.
And what happens near the origin is an immaterial because it's all up to unitary equivalence anyway.
Exactly. Yes. Exactly. So everything's up to unitary equivalence. So you can always move it just far enough in the cone, indeed.
That's right. You can have fuzzy strings instead of this very.
Yeah. So the only issue that you really can get is when you start perturbing the model, when the strings get a little bit fuzzy. So there will be some decaying tails, and then if you go farther, the tails might decay a little bit further. But that's something you can control. That's something that I will talk about on Thursday. Yeah. But yeah, this as I said before, this notion. So it doesn't matter too much that it's a cone, and you might, if you work in a different dimension or you work in with different kind of excitations, you might want to change this notion of what you mean to be localized. Let's say this is the right one for us. Good. Right. So let's make some comments on this. Right. So these automorphs are defined earlier. They are in this category, basically by construction. If you have something in this category I just defined, again by definition, if I compose by 0 with this row, I get a representation to satisfy the superselection criteria. An important part is that this category, it actually depends very much on this choice of pi 0 as a reference representation, right? Because you have this, for example, this condition on the intertwiners, and that's where the dependence on pi 0 comes from. So maybe that's a good point to remark. So I didn't really use the dynamics of the Tor code anymore. So basically, the only way that I really use the dynamics is, well, this dynamics gives me a ground state, and I can use this representation, this ground state representation as my reference representation, right? I don't really need that it actually comes from a ground state. So somebody can just give you a representation and ask, what are the sectors with respect to this representation. So yeah, it's only the dynamics only really comes in by choosing the right choosing the right reference representation. And of course, in our case, it's also important because it gives some idea of what of which sectors to define, right? So that's we use the dynamics to define these things to give the right representation. But if you don't know the model and you just get the representation, you can still do the same thing. Right. Good. So yeah, we want this to define this tensor product on this category, but it's not just a subcategory of our endomorphism of A. And the reason is because our morphisms in the category, namely the intertwiners or the charge transporters, they are not in the algebra A anymore, but now they are in B of H, on the representation space. So they live in a different algebra. And in general, they are not going to be in the image of pi 0 of A. So they don't really come from our algebra A. And that's of course an issue because I defined my monoidal product. What I had to do is I had to act with my endomorphisms or my automorphisms on these intertwiners, right? But now my intertwiners live in a different algebra, so this a priori is not defined. Good. So fortunately, we can do something to work around that. And yeah, so that's to do that. Let's have a look again at these charge transporters. So I've shown you, based on an argument on the uniqueness of the GNS construction, that these unitaries exist. But we can actually do something much more explicit, namely I can find some sequence that converges to this unitary in a nice topology. Right, so let me briefly explain this here. I'm going to show you a picture soon that makes this a little bit more clear, I think. But yeah, so without lots of generality, again, we can look at something that starts at the same endpoint. Actually, I think my picture doesn't do that. That's okay. And we look at these corresponding automorphs. So these two semi-infinite ribbons, right. Just a little bit of notation. I write just subscript n for the ribbon or path operator. I should really say path operator. So subscript n just means you take the first n bits of it, and then of course if n goes to infinity, you get the whole thing. Right. So what am I going to do? For each of the n's, I'm going to connect these two different paths with the new path psi n hat, and I want to do this in such a way that this path goes further away from my x. Right, so I'm going further away out from my original path. I go from one to the other and back, and then as my n grows, I go further away. Right. Good. sorry, this definition is not quite right here. So so what I'm going to do now is I'm going to define f of so this should not be psi n, but this should be the concatenation of psi n hat, and then psi n prime in the other direction. I will show you the picture soon, but this gives you a path operator, and if I take the limit of that, so you have this intertwining property. So the interpretation is that this Vn, what it does, we have this excitation here, we move it back along the one path, then we go over to the other one, and we move it back to the other one. So that's the picture that we have here. So as I said in my picture, they don't start at the same point, it doesn't matter too much. So I move this excitation along here. You can do that with the same path operator. Then I move it with the path psi n to the other one, and then I go back along this way. So that's what you can do. So in the case for the toric code, like moving one way and the other way is basically the same. You have to be a bit more careful. You have to take care of the orientation in the more general case, but that's not too important. But yeah, the property that I wanted of this psi n hat is basically these connecting bridges here. If you want, they should the distance to here should go to infinity, so they should really move out. So really, maybe sort of an intuitive way of trying to think about this is that I'm moving this anion from one brace to the other one, but I'm going via infinity, via this limiting procedure. That's the idea. Right. Good. So that's a sequence of operators, but this sequence will not converge in the norm topology, so it will not be an element of my C-star algebra A. So I have to talk a little bit now about operator algebras, and in our case, polynomial algebras, because they behave kind of like. Right. So a definition. So there's many ways that you can define a polynomial algebra. This is sort of the easiest one to define it. So you take a Hilbert space, you take some subset of the bounded operators on this Hilbert space, and you want the subset to be a unital star algebra. And then we say that M is a monoidal algebra if M is equal to its double commentant. Right. So the commentant, so the prime here denotes the commentant. So it's the commentant of this M inside B of H. You calculate that, you do that again, and if you get M back, then we say it's a monoidal algebra. Right. So in this definition, it doesn't really matter that it's unital because, of course, the unit always commutes with everything. So this will always be unital if it's true. But for the following theorem, it is important. So yeah, so there's many different ways, as I said, of defining a polynomial algebra, and basically they're characterized by this by the Newton theorem. Right. So we have here a Hilbert space. And the bounded operators of the Hilbert space, they have quite a few different natural topologies on there. And a polynomial algebra, so M is, as it turns out, is a polynomial algebra if and only if it's closed in what's called the weak operator topology. So that's topology of so X lambda converges to X in the weak operator topology, if and only if all these expectation values go to 0 for all vectors phi and psi in the Hilbert space. And this is equivalent to saying that M is closed in the strong operator topology, which is the same with convergence when you act on the vector. And there's at least 4 more that you can write here in this, but these are the main ones that we will use. Right. So for this to be true, you need this to be unital, otherwise you kind of can cut down on the small space. But, right. So that's what the polynomial algebra is. And so why do we care about these polynomial algebras? Well, as I said, the sequence that I wrote before that should move this charge, it does not convert in norm to an element of A. However, if I compose this with the if I act with the ground representation on this thing, so I get a net of operators on the Hilbert space, it does converge to a unitary even in the strong operator topology, or in the weak operator topology as well. There's different topologies you can use to do this. And let me just give you, excuse me, let me just give a brief sketch of how this goes. Right, so if you take a local operator A, so again, I use the convention here that I don't write the pi 0 because it's injective. So you can just think of all pi zeros here. So if you take a local operator A and I act on the omega, this will give me a dense subset. So you can show it's enough to show that actually this is a co-sequence for all these A and log. So essentially what the idea is you have this local observable A, that's now a restricting local one. So it will have finite support. And we have the sequence of these paths, and you're just going to make sure that you go far enough away along this path, such that all the new paths, psi n, that connect these two things, are away from A. So you just go make sure you're far away enough. So let me just maybe go here in the picture. So let's say if your A is somewhere localized over here, like everything from here on, these paths will always be outside of support, right? And because of this thing of going to infinity, you can always choose some n, so that for all the bigger n, this will be the case. Right. So another way of saying that is the support of this path operator intersection with the support of A will be constant at some point. Right. We can write our path operator before as product of the three path operators. So we take the first parts of these two infinite strings that we started with, and then the last one is this psi n that connects the two. Well, it goes like this. But yeah, essentially what we get here is we get a string that is finite on both sides, and then we look at a new string that connects these two finite endpoints that goes to infinity. Right. Yeah. So and then we can use this property that I mentioned earlier, namely if we act with a string operator on this or a path operator on the ground state, then the state it does not depend on the precise path, it only depends on the endpoints of these two things. Right, so I have these two endpoints fixed now. I just make this loop longer and longer, but acting on the ground state, that does not change anything. So this is the calculation that we get here, V and A of omega. I just use my K big enough. I take the first part, K parts of my path psi, the first K part of my path psi prime, and this psi and twiddle goes further along the path to the other one and back. So this ones, they will all have the same endpoints, but by choice of these paths, the support of this one will be disjoint from all the other ones. So these operators all commute to there. I can bring it all the way to the right hand side. Now we can use the independence of this vector. Only depends on the endpoints, which are fixed. So we get that the sequence eventually becomes constant. So particularly the sequence. Right. So that's again using this locality to do that. Right. Right. To get it to actually show that the unitary, you have to do the same thing for the adjoints. In this case, it doesn't matter because all these operators are adjoined, but that's what you do in general case. Good. So what do we get from this? Well, I just told you if a Neumann algebra is closed in this strong operator topology. So it follows that V, that's the well, it follows that this sequence Vn converges to some V, and this is in the Van Neumann algebra generated by this cone algebra. So that's right. So from the definition of a Van Neumann algebra, it's easy to see if you take any star subalgebra, you take a double commutant, you automatically get a Van Neumann algebra. This is the smallest Van Neumann algebra that contains this algebra. Right. And because of this closest property, this is in there. And it's an intertwiner, as I already indicated. So yeah, so these charge transporters, they don't live in our C-star algebra, but we still have good control of them. Maybe we can recognize them in this kind of Van Neumann algebras. So they're bigger, but we still have some control over it because we still have this weak there. Right. So we can imagine that these algebras are going to be important, and indeed they will be. So I want to introduce some notation for this. I will call this a cone Van Neumann algebra. So if I have a cone, I can look at the image of all the observables in the cone, and I can look at the associated phenomenon algebra. Right. Good. I need another technical property, and this is called Haag duality. So what is this? Well, we say a representation by 0 of A satisfies Haag duality for cones if we have this equality. So on the left-hand side, we have the phenomenon algebra generated by the observables in this cone. That's the one I just wrote down. You can look at another algebra, namely, you can look at all the observables outside of this cone. This is an algebra. I can take the commentant. This is automatically phenomenon algebra. Again, you can check this. If you take the double commentant of this, you get the same thing back. And I want these two things to be equal. Right. So that's what's called Haag duality. You can show that this holds for big and quantum double models. It's most likely holds for much wider class of models. Then let me not say too much about this at the moment. So let me just make one more comment. Is that this inclusion, this always holds by locality, just by locality of the observables. The other one, that's kind of the hard one. So yeah, so this takes some work to prove, but it's true. But yeah, if you're not sure about this Haag duality, I just maybe want to stress that in the example of the Tor code, for most of the analysis, we don't really need this. As I said before, so most of the things we can actually construct explicitly by this charge transporters. Good. So I want to give some applications of this Haag duality. So the first one is localization of intertwine. So I just constructed these intertwiners explicitly as weak limits, and this in particular gives some localization. But if you don't know, if you have a model where you don't know how to construct these things, this can help. So what's the statement? So suppose you have two different cones, and they are contained in some larger cone. And I have two of these representations localized in lambda I. So this just means that they're equal to the constant representation outside of these cones. If I have an intertwiner between them, then this intertwiner is going to be in this cone phenomenon algebra. Good. The proof is quite simple. So consider something in outside of this big cone. Then we can have this short calculation. So I want V by 0 of A outside of this cone by 0 of A equal to rho 1 of A. V is an intertwiner, so I can bring it to the other side. So go and rho 1 becomes rho 2. And then I go backwards. Again, A is outside of the cone containing these two things. So this is rho 2 is equal to twice to A as well. So what we see here is that V is in the commentant of this thing. Right. So that's what I say here. And by Haag duality, this is equal to this thing. Right. So that's again a way to localize the intertwiners, and that will be important when we define the tensor product. All right, I see my time is almost up, so I think I started 5 minutes later. So I will try to be very brief here, but I want to get to a point. It's natural to stop. So this is I think an important point as well. So before we constructed explicit examples of these automorphisms describing things. Right? So let's suppose now I want to go the other way around. So I have some representation pi satisfying now the superselection criterion. Can I get back from that something like an automorphism or maybe an endomorphism or something like this? So the answer is no, but at least not directly, but it's something very close, and that will be good enough for us. Right. So what's the statement? I have some representation satisfying superselection criterion, and I can find an equivalent representation of A on my GNS Hilbert space from the ground state. So this might have been on different or defined on a different Hilbert space, but I can always find something equivalent that's defined on my ground state Hilbert space, such that rho lambda of A is equal to pi 0 of A, where lambda is the choice of cone for all A outside of this cone. So there's rho lambda is going to be localized in this cone lambda. And the other property that I want to have is that if I have something in the cone, then it sends the image into this monoidal algebra. Right. So it's not quite an endomorphism of A, right? So outside of the cone, it's fine. It just maps A to itself. But if you have some observable inside of the cone, it might not map this thing inside of the cone algebra again, but it will map it into this slightly larger Neumann algebra. Good. So how do we prove this? Well, by the superselection criterion. So I pick a cone, and by the superselection criterion, there should be some unitary such that this holds. So this is just writing out what it means for these two representations to be equivalent outside of the cone. So there's this unitary, such that this is equal like this. I'm going to define rho lambda of A in this way. Oops. So this is a unitary. So this is going to be a representation again. And if I got my stars in the right place, I think I did. So this is indeed a representation on wait, so the things go the wrong way. I think that started in the wrong way, but yeah, because this is not defined here. So this should be a pi, I think. Right, but anyway, so we get an equivalent representation from A on B B of H0. Yeah, so this should be a pi because of course it's going to be equivalent to pi. Right, so we know that for A outside of the cone, this holds. But we want to say something about A inside of the cone. So what we do again, we take B outside of the cone, then we have the short calculation by 0 of B rho lambda of A. So this is just inverting this thing here. So this is just this thing for this holds outside of the cone. This is by definition. So as I said, this should be pi. Right, so here we have a unitary, so this cancels out. We have a representation, so this is equal to pi B of A. A and B, they live in, one lives inside of the cone, one lives outside of the cone. So they act in different parts of the system and commute. So I can take them like this, and I go back in the other way. And I have this thing on the other side. Right, so now we can again apply Hague duality to get the conclusion. So we have something in the commentant, and we know the commentant is equal to this thing. Right, so that's the other application. So let me finish with this slide, and then tomorrow I will continue with this. So this is basically just saying what I just said, right? So before these automorphisms that you constructed, they had the nice property that they actually map the algebra into itself. So in this case, we don't quite have that, but we mapped it to a slightly different algebra. But we do have good control of the localization. So what's going to be the idea for tomorrow? We want to mimic this idea of this end of A tensor category, so where we compose these things. Now we just have representations, we cannot compose representations. But what I want to show is that instead of this representation, we can look at endomorphisms of a slightly larger algebra, so slightly larger compared to this one. That's equivalent. And then once we have endomorphisms, we can do the same things like that before. Right, so my time is up for today, so let's do that tomorrow. Thanks.